Hello, everyone. This is Yao. I'm going to present the paper Plasticity-on-Chip design, exploiting self-similarity for data communications. This is the outline of the presentation. First, I'm going to briefly have an introduction and motivation. Traditionally, the design hierarchy we have is always bottom up. So is always bottom up, meaning hardware design is designed first, and then software uses hardware. One of the drawbacks is that software performance is not optimal, as it may not have a clear picture on how to spawn threads for parallel execution. Therefore, we believe that instead of bottom-up, top-down is another view of the design hierarchy, which helps for system performance. However, we need to have intelligence in hardware to recognize the change of software and how this change would affect the overall performance. During this presentation, we will answer a few research questions: how to model and mine high-level applications, how to design an irregular deadlock-free network on chip, how to efficiently synthesize and map communities onto hardware. The trick to all of the questions is to represent applications as complex networks and analyze their structural information to understand program properties. Next, we are going to understand that programs have their own topological structures, which exhibit self-similarity. So one example is iteration. We can see that we have two different structures. This is star structure and this is mesh structure, depending on how iterations are implemented. Nevertheless, both exhibit self-similar fractal structures, where in the star structure, if we zoom in a little bit, so probably this portion is also a star. And in the mesh topology, if we zoom in this graph, like this portion, it is also a mesh topology. And these fractal topological structures can be measured by the fractal dimension, which we'll discuss later, but it is the slope of the fitting line, as you can see here. Another example is recursion. We can see that the structure of one representative program is tree. So the program we use for this one is Fibonacci, which also shows fractal topological structures. If we zoom in a branch, it is also a tree structure. And it can also be measured by the fractal dimension using this plot. Real-life applications can contain both iteration and recursion because those are two fundamental programming strategies and have a hybrid of different topological structures in graph. So if we take a look at probably this drone controller, so this portion can represent a mesh topology, and probably this one so have a star structure in it, or this one. And where we can also measure the fractal dimension using the plot on the right hand side. In this presentation, we will present Plasticity-on-Chip, which includes 4 parts: communication modeling, optimal parallels discovery, fractal dimension and the degree distribution, and the process element mapping. We first construct the power law distributed graph, which is abbreviated as PDG. So N represents instructions dynamically generated at runtime. E represents the control data memory dependency as edges. W represents the community cost. This is one example of how to construct the graph from ARVM-IR instructions. We have a compiler-based parser to parse one line and add this node into the graph. Then check if source register of this instruction depend on the destination registers of the previous instruction. So basically, this is the data dependency, but we have also data control and memory dependency. So let's say if we have this data dependency, then we add an edge in between. So this one shows you how the graph basically is constructed. Next comes community detection. What is a community? So it is a dense subgraph exhibiting common patterns. Communities implement heterogeneous functionalities. So in hardware, there may be some required processing elements. In networking, they may correspond to groups of people with the same interest. So therefore, community detection is an approach to find out communities in a network. As you can see in this figure, we clearly have three communities, 1, 2, and 3, where nodes are densely clustered together, such that inter-community communication is minimal. So let's take a look at the optimization model used in optimal parallel discovery. So given a SPDG represented as a complex weighted network, so we want to find non-overlapping clusters. So these can be computational or processing communities, which maximize a quality function. So which, as you can see before. So basically, we want to partition the graph maybe into the following community graph. So let's take a look at the three terms used in this optimization model. So the first term restricts data communication within each community. So this is the sum of weights in a cluster. And this is the inter-cluster weight sum. So basically, by maximizing R1, we're trying to maximize the sum of weights in a cluster, basically trying to restrict data communication in each community. And the second term guarantees an acyclic graph, where because we want to minimize, we want to maximize M. So in return, we want to minimize R2 and R3. So if we want to minimize R2, then it means that we want to, so we don't want this edge factor happens at this time. So by allowing this no backward edge, so we guarantee a cyclic graph. And then the third term limits the number of input and output edges in a community. So one of the motivation in R3 is that the buffers used in input port and output port in a router is very energy consuming. So we want to minimize the number of ports used in a router. So therefore, we want to minimize R3. Next, I'm going to briefly talk about fractals. So fractal is infinite iterated self-similar mathematical construct. So basically, we want to, and it is characterized by fractal dimension. So we want to find the fractal dimension for each graph. And one of fractal analysis is used to determine the fractal dimension of an object using the box covering method. The idea is to use a box of a fixed length to cover the object and record the length and then the number of boxes to fully cover the object. Then we can use the linear regression, as you can see here, to find the curve and calculate the slope as the fractal dimension. So next I'm going to show you an example. So let's imagine we have this object where it can represent a graph. And initially, we can use a box of a unit size to cover the object. And then clearly, the number of boxes to cover the object is 1 in this case. And however, if we vary the box length, so imagine this time we change it to 0.5 unit length. And now, as you can see, the number of boxes to cover the object is now 3. It is not 4 because here a graph, we don't have anything to cover the object. And then we further use a 0.25 unit length as the box length. And the number of boxes to cover the object is now 11, as you can check. And then, we use 1/8 unit length, and then the number of boxes is 26. And finally, we collect all the results and put it in a graph. So basically, the x-axis is the box length, and then the y-axis is the number of boxes. We have different points here. And then we use linear regression to find the curve, and we calculate the slope as the fractal dimension, as you can see here. Next, we propose a deep reinforcement learning based mapper. So the input to this mapper is the community graph, as you can see in this one. The output is the actions, such as mapping one community to a processing element. So fractal dimension and also degree distribution are used as features in graph convolutional neural network. Graph convolutional neural network is acting an agent to receive the states and rewards from the environment, which is plasticity-on-chip, and output actions to act on the environment. So in this deep reinforcement learning based mapper, we need 3 components. The first one is a set of environment states observed by the agent. So which we use locations of available process elements and then the buffer sizes for routers. And next component is a set of actions performed by the agent. So then we use the mapping of tasks onto PE. So probably this parallel task can be mapped onto GPU, whereas the sequential task can be mapped onto CPU. So as you can see here. And the intermediary reward takes into account the execution time of a task, buffer sizing, and the energy consumption of this task. Next, I'm going to briefly talk about the evaluation and conclude this presentation. So let's discuss the experimental results. We use CPUs. CPUs with 32 CPUs and 32 GPUs. And this is the configuration parameters we used in the evaluation. And we also compare our framework with Gen 5 Aladdin, Min BD, and also SOS PCS. So in terms of application speed up, so we have 2.6 improvement compared to Gen 5 Aladdin, and 7.61 x over the baseline because of the restriction in data movements within a cluster. And in terms of power improvement, so we have 1.86 on average compared to Gen 5 Aladdin, and 1.53x on average to MinBD. So let's conclude this presentation. So we provide an POC design flow for future platforms, scalable to understand the fractal structures and the dynamics of high-level programs. And the experimental results on synthesized PE and NOC shows performance improvements as high as 7.61x when compared to traditional network on chip, and 2.6x compared to Gen 5 Aladdin. Thank you very much.